Hi everybody, this is a mini lecture answering the muddiest points on DMA timers. First off, I'd like to answer a very important question that I got, which was, how do I even? And the answer I have for you is, you must really go far. Even as you decide to use, you want to do more. So I hope that really clears that up. Moving on, these are the questions that you guys mostly had, focusing on GPIO, using the IMRM, and bitwise operations. I actually have a video focusing on that, so already posted. So if you want to see answers to those questions, please click on the orange box on YouTube, and it will take you directly to the other video, and you can watch that and get an idea of how to do that. And as always, let me know if you have any questions about the specifics of those. What's left, this little timer section over here. So this video is going to focus on how to use the timer and how the timer works and how everything works there. So let's look at how the DMA timer works. First off, it takes an internal bus clock, right? So a timer is really just a counter that counts event transitions. And in this case, the event transition is the cycling of the internal bus clock or some input from the outside world. If it's the internal bus clock, we know that this clock cycles at a known rate. So if we can count how fast, if we can count how many ticks have gone past, then we know how long in real time the timer has been ticking, right? And what that does, here we generate the clock signal based on either the system clock or an input clock. We generate this clock signal by dividing it by some divider value, which is the prescaler, and we have some mode bits to control the system. The divider feeds the counter register. So what happens is the internal bus clock, or whatever our clock source is, gets divided by some value here. The frequency is divided by some value here, and then when and then we have a slower tick rate here. That feeds into our timer counter register. So every time this wire ticks up high or transitions from high to low, this increments one value. Then we have a decision as to whether we're doing capture detection and it would take this path, or if we're doing a reference match, which it'll take this path. And basically what happens here is when the timer counter register is just one greater than the reference register, then it sets an event bit in the event register, which is the reference match bit, right? So to look at this in more detail, we're going to look at a simulation really quick. So here we have a simulation of the hardware that is performing the timer operations. We have a clock source over here, and this could either be the internal system clock or an external clock source. We have a scaling system with a scaling setting. We have the counter register, we have the reference register, and we have some comparison hardware. And what's happening here is we can see that the clock source feeds the counter. The clock source feeds the prescaler hardware, which divides the clock by whatever value we put into these bits here, which would be in the DTMR, the mode register, in our actual hardware. Then we have a clock out, and this is divided. So for instance, if we have 0, 0, 0, that means that the clock is basically divided by nothing. It's whatever clock source it is. So every time the clock ticks up, it ticks up once on the clock out here, right? If I put in, say, 2 here, then it's going to tick every other time. So I click up once, I click up again, and it transitions. Click once, click again, it transitions. 1, 2, 1, 2. And each time, it increments the counter register, right? So I'm dividing my output clock, I'm dividing my input clock by whatever value I put in here, and that makes the counter tick slower, right? Then in the reference register, I can set what value I want to put in here so that when it exceeds or is greater than this value, then the reference match bit is set. So let's just say, we'll put A in there. We'll say it's 10. So in this point, whatever I have in the reference register is compared with whatever is currently in the counter register, and that sends the reference match bit in the DTER register on our main system. So as I tick these, along, we'll see it transition, and when it gets to 10, we should see the reference match bit get set. Now notice that they're equal, but it hasn't triggered yet. That's because the hardware itself actually looks to see if the counter is greater than the reference register. So it's going to be one tick past, one ultimate tick past that it's matched, right? So I've been clicking this a whole bunch of times, right? Probably 20 times, and it's finally ticked 20 times past, even though I've only counted 10 ticks. So this is in ticks of whatever units is going on here. And then there's some extra hardware down here for reset and whether or not we're going to, we want it to reset automatically or free run, where the timer will keep ticking even past the event, right? Now that we know how the timer works, I want to go through and walk through the code on how we make this thing actually work from software. So what we're going to do is we're going to look at the code that we generated in class, and we're going to step through and see how it affects the hardware specifically, right? So first off, we're going to be looking at the DTMR register. This is the DMA Timer mode register. And the first few instructions, what they do is they force a reset. So if we go and look at the documentation for this particular register, it talks about the RST bit, which is the least significant bit in the whole register. And you'll notice that I've got masks and values here that are 4 nibbles wide. That's because this is a 16-bit register. The first 4 bits are the lower nibble, then the next 4 bits are the next nibble, and then the top 2 bits are the top 2 blocks of 4 are the upper 2 nibbles. So setting using a 1 here, and the OR equals, we're self-ORing, so it's DTMR ORed with itself and whatever this is, right? So this value is 0001, which sets a single 1 bit in the RST region here. To initiate a reset of the whole module, to reset all the registers, we have to transition from 1 to 0. So this starts out as 0 by setting a 1 and then transitioning to 0 with the next instruction. As we'll see here, we set it to 1, then we transition to 0. That resets all of the modules in the other system, and all the other bits aren't affected. They should all be the same from this. What this next piece does is also modify the other bits in the mode register, right? And if we break it down, we can see that we set a bunch of different bits here. So we have a 4F02, so that's going to put a 4 in this nibble, an F, which is all 1s in this nibble, zeros all in this nibble, and then a 2 in this nibble. So the RST bit is going to stay the same, but that's going to put a 1 right here in the clock section. What this clock section is our clock select. And if we go and look in the data sheet or in the IMRM for this section, it talks about what clock source this is. It's going to be our system clock source, which is running at 80 megahertz divided by 1, which is what the value that we put in here is. We put a 1 in here, and that selects our raw 80 megahertz clock source, right? Then we have free running, which is 0. These are all 0. We don't really care about what they are. And then we have the PS stage here. And what the PS stage is our prescaler. It's what we're dividing the raw clock by to get how often the timer is going to tick, right? And it gets set to this. So we have a 4, an F, and then a 2 in the lower nibble here. So let's look at how we calculated our prescaler value of 4F, right? To choose our prescaler value, we need to look at this equation. This is at the end of chapter 6, I believe. No, it's at the end of chapter 26. It's at the end of chapter 26, and we have how the timeout period relates to the system clock frequency, whether we're dividing by 1 or 16 by the clock frequency. We're dividing by 1, and then the prescaler for the system, and then whatever our reference register is. You'll notice here that the prescaler is that the timeout period increases as the prescaler increases at the same proportion. This means that we're dividing our clock frequency by this value to get a slower clock if we put a larger number in here, right? Our goal is to be able to set the timer to measure delays in microseconds, right? And we know that a microsecond is we want the timer counter to increment by 1 every 10 to the negative 6 seconds, or increment with a frequency of 1 megahertz, 10 to the 6 hertz, right? Our system clock frequency is 80 megahertz, which is 80 times 10 to the 6th. And if we divide those, we know we need to divide or scale our system clock by our source rate divided by our target rate, which is 80. Right, so we want to write 80 into the prescaler, or so we think. Notice this plus 1 here. Because this plus 1 here is here, that means that if we put 80 in here, it would actually divide the system clock by 81, which is not what we want. So to divide it by 80, we have to put 79 into the prescaler, and that'll give us exactly what we're shooting for, right? So we want to write 79 to the prescaler field of DTMR, and that gives us the 79 is a hex of 4F, and we just put those in the upper 2 nibbles, and that gives us exactly what we want out of our code here. And that's why we got 4F02 instead of what would be 50, which would be 80 in hex. Okay, so next we want to set the halted bit, and what this does in this line right here is set bit number 6 in the DT XMR register. It's the extended mode register, and all this says is that when we're in debugging mode and we break on a breakpoint, it stops the timer rather than letting it run, which is what we want. Okay, so that's the initialization function. That sets everything up in the module to be used. Next, we want to use this thing, right? So say from main, we call d times 0 delay 1700, right? We want to delay for 1.7 milliseconds, right? A millisecond is 1,000 microseconds, so we would put 1700 in here. Now what this does is it calls this function right here, and the first thing that this function does is clear the events. If we look at what the DTE are, the DMA Timer event register, what it does is has a couple of bits here that get set when an event occurs, right? And because we're about to wait for this event, we want to make sure any previous events are cleared. So to do that, we don't write zeros into that. That's what this little thing here means. When it says W1C, that means write a 1 to clear, which is kind of confusing. But basically what happens is here we've got 0x03, and we know that that's 1, 1 in binary. So we're going to be writing 2 1s into those 2 bits of the register. What the hardware does is it sees those 1s and it interprets that. Instead of triggering an event, it actually clears any previous events and automatically transitions them to 0. So this writing 2 1s into those bits makes sure that there are actually zeros there, right? The next instruction clears the timer counter, right? That's all it does is reset the timer counter to 0. Then the next instruction after that sets the reference register to U-1. And you might be asking why we subtract 1 here. The reason why is because we want to look back at this equation again. Again, the timeout period is going to be, if we have our clock set up to be ticking at a certain rate, it's going to be however many ticks are in the reference register plus 1. So if we put just our 1700 in there, it would actually count until 1701 rather than the 1700 specifically that we're looking for. So we subtract 1 here and set our reference register to do that, so that when the timer counter reaches 1699, and then 1700, the event bit, the event register bit flag will be set, and everything will be exactly where we want it to be. The next thing is that we want to set the reset register. And what this does is actually sets the clock to running. If this is 0, the clock is stopped and nothing is happening. But if we set it to 1, that actually starts the timer counter register incrementing, and we can start timing values with that, right? The next thing is we're watching, as soon as that bit is set, the timer counter register starts incrementing at 1 megahertz, so 1 cycle per microsecond, right? And we're just waiting for this timer counter register to be equal to 1 plus the reference register, and that'll what that'll do is it'll set, the hardware will automatically set this reference bit, and that's what we're waiting for in software here. So in software, we're waiting for a 1 to show up in the reference bit, and if it doesn't show up, then we're just going to keep waiting. We're just going to keep doing this nothing loop, right? So it just hangs here forever until the reference bit is set and we can move on. As soon as the timer counter register gets close at 1699, and then at 1700, the ref bit gets set. The while this statement right here becomes false. Actually, it becomes true. This statement right here becomes true. Then it's inverted here, which makes it false, which causes the while to break out, and the function returns. Pretty simple, right? Okay, so that's our walkthrough of the DTime0 module. Please let me know if you have any further questions, and I'll see you guys in class.